Hi everyone, welcome to the Data Idols Summer School and welcome back to our community who have been following us for the past 5 years. I'm Courtney and I'm a recruiter here at the Data Idols. The Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months so you can learn in real time and pick up new skills from the comfort of your home. These sessions are ideal for people transitioning into data or for those starting their career. Please use the Slack channel if you're watching this session live to chat with other attendees. The link will be in the chat soon. Thank you to all of our partners who made this event a success and for the 400 plus hours it took our team to make the summer school a reality. All sessions are pre-recorded and can be watched back at a later date starting in September. We will be emailing you with a link to watch the sessions back September 1st and they'll be free to watch. So if you miss anything or want to learn at your own pace, it will be available at this time. Today, our session is feature selection for machine learning with Soledad from Train in Data. Thank you for supporting the Data Science Festival in partnership with Data Idols and enjoy the session.
Welcome to the summer school. My name is Soledad Galli. And today I'm going to be talking about feature selection for machine learning. First, let me tell you a little bit about who we are. In Training Data, we are a group of data scientists and Python software developers, and we have been in the industry developing and deploying machine learning models for a while, and throughout this time we have encountered a number of challenges and therefore developed a number of solutions. And we decided to put all this knowledge in several contexts, like, for example, online courses, books, and also open source packages, hopefully to help the community troubleshoot these challenges easier and faster. You can find more about this content and ourselves at trainingdata.com. So with this said, I would like to first set the framework of what we're going to discuss throughout this video. Machine learning is used quite widely throughout the industries. For example, we use machine learning to predict the fate of insurance claims. We can also use machine learning models to identify fraud. We create machine learning models to assess credit risk before, for example, disbursing a loan. We also use machine learning to anticipate the demand of energy and also to forecast the production of energy, and this is particularly useful in the era of renewable energy. We can also use machine learning for things that are less interesting, in my opinion, like, for example, marketing. We can also use it to produce a better premium for an insurance and to anticipate if a customer is going to leave our company and to go into a competitor's company. In a high-level overview, we have data in several places, like, for example, in a cloud, like AWS, or we can have databases where we store our data that we collect somehow from customers or our interactions. And we can also get data from third-party APIs, typically companies which product is data, like, for example, credit agencies. So we would collect all this data and we will use it to train machine learning models, hoping to make the predictions that we're interested in. Now, the data will have a lot of variables. And if we're planning to use this data in real life, we probably don't want to train the models utilizing this big number of variables. And there are a number of reasons for this. Once we start analyzing the data, we will soon realize that a lot of our variables are constant. This means that they only show one value for all the observations. Some other variables are what I call quasi-constant, which means that the great majority of the observations will show one value and only a small proportion of observations will show a different value. We will often encounter variables that are identical, even if they have a different name, so there is a lot of duplication. And we will also find a lot of correlation in our variables. This is the highest the value of one of the variables, the highest the value of the other variable. So in essence, these variables are producing or are providing the same information. So there is no reason to use all these variables to train machine learning model when they provide no or redundant information. So in order to reduce the number of features, we use feature selection procedures, and feature selection is in essence the process of selecting the most relevant or the most predictive subset of features in our dataset to train the machine learning models. Now, why do we want to select features? Why don't we just use all the features that we want? And that would certainly seem easier at first sight, but not really. And there are a number of reasons why we would select features if we're actually intending to. First, simple models, so this is models with less features, are easier to interpret. When we make a prediction, for example, we say that this claim may be fraudulent, someone is going to analyze that claim. And then it is easier if we have simple models to understand why that claim is fraudulent, which features are suggesting that this claim is fraudulent. If you have 10 features, it's an easier situation to interpret than if we have 100 features. Second, shorter training times. If we train a model on 10 variables, it will train much faster than if we train it on thousands of variables. And at the same time, and more important, if we're going to use it in an application, is that it reduces the prediction times. So we can provide answers quicker. It may produce enhanced generalization by reducing overfitting if we remove a lot of variables that are just adding noise. One key issue, at least in my opinion, is that simpler models with less features are easier to put in production by software developers. And this is because there is less code to code in order to pre-process all these features, less testing to add, less error catchers. And because of all of this, it reduces the chances of the lack of reproducibility within the research and developing environment. The less number of features, the less we are susceptible at errors that occur in the APIs where we obtain this data from. Particularly, this is important if we're using data from third-party companies. If the company servers shut down, we are vulnerable. If we have a lot of features, we are very vulnerable. If we're using just a couple of features, we're not so vulnerable. And the last one, as I explained previously, data redundancy, duplications, correlations. So if I manage to convince you that less is more, then the next problem is how do we select the variables? How do we find the variables that are the most predictive or the variables that produce the most predictive algorithms? Well, there are a number of feature selection methods that we can use, and they are grouped in 3 classifications, if you want, based on the underlying characteristics of these methods. We have on one hand the filter methods, we have wrapper methods, and we have embedded methods. And if there is a method that doesn't fall right within one of these categories, maybe it have characteristics of 2 of these categories, it lies right in between, is what I call hybrid methods. Fortunately, open source libraries support the implementation of the great majority of the feature selection algorithms that we find or that we know of today. Scikit-learn offers support for filter and embedded methods. MLXtend offers support for the wrapper methods, and Feature Engine will allow us to implement hybrid methods of feature selection. So throughout the rest of the video, I will dive in to each of these characteristics, each of these groups of methods. We will understand what is the common characteristic that they share, and then we will describe the several algorithms within these groups and how we can implement them with Python open source. So let's move on to filter methods. I'm going to start talking about univariate filter methods. This is methods that look feature per feature to determine a ranking of feature importance. Filter methods have 2 main characteristics. The first one is that they are independent of the algorithm. So in order to rank the feature or to determine the importance of the feature, we're going to use very often a statistical test, like I will show in this next slide. And these tests are classic statistical tests, so they are independent of the machine learning algorithms. And they basically rank the variable just looking at that particular variable. This has a number of pros and a number of cons. On the pros is that it is model agnostic. So in essence, the group of features that we select with these procedures should work for all machine learning models. So if we try random forest or linear models, it should be roughly the same. And because they are very simple statistical tests, they are performed fast, they are fast computation, and then they give us a tool to quickly remove useless features. On the downside, they look feature per feature, so they will not detect duplication, so they cannot cope with data redundancy. And they, for the same reason, they will not detect interaction between features, just because they look feature per feature. And at the end of the day, these methods return the subset of features that return the poorest model performance. So filter methods are really good because they are fast if we want to quickly screen our features and maybe quickly remove the most useless features, but at the end of the day, they will not produce the best performing model that we're going to be able to develop. Filter methods have two steps if you want. The first step includes a test or an algorithm to rank the features based on some parameter. And the second step is to select the top ranking features based on some other parameter. So in order to rank tests, we can use statistical tests, like for example, chi-square. If we have categorical variables, chi-square determines the distribution of categories in two groups, and one group could be when the target is 0, and the other group is when the target is 1, or if we have multi-class. So it allows us to say the distribution of categories in the different segments of the targets are the same. If they are the same, then the p-value is going to be really big. If they are not the same, then the p-value is going to be really small. So it's ranking of features. A similar procedure for numerical variables is utilizing ANOVA. And this we can use for discrete and continuous targets. ANOVA assumes a number of things about distributions of the variables that we're testing. So we, instead of using ANOVA, if these assumptions are not met, we can use another statistical test, which is the mutual information. And then also supported by scikit-learn, as we will see in a minute, is the variance. So here the assumption is that features with higher variance are more predictive than features with lower variance. And the extreme case here is the constant feature, where it offers one value for all the observations. So the discriminatory power of this feature is virtually 0. So filter methods first rank the features, determine a ranking metric for every feature, and then select the top ranking features. We can implement this with scikit-learn. So scikit-learn will offer classes to rank the features. For example, chi-square to perform chi-square, f-classif and f-regression to perform ANOVA when the target is discrete or when the target is continuous. And if we want to perform the mutual information, we use the mutual info classif or the mutual info regression. And if we want to select features based on the variance, we will use the variance threshold. So these classes will rank the features, and now we need another class to select the top ranking features. Scikit-learn offers select k-best to select the k top ranking features, and select percentile with select the features in the top ranking percentile. Here, k, or the top percentile, is to be defined by us. If the bigger the k, the more features that we select, and the smallest the percentage. So if we choose the top 10 percentile, we will have less features than if we choose the top 20 percentile. With the generic univariate select, we can select features on any user-designed way of selecting features. For example, we can select those features which ranking is above the mode of all the features. And to implement this with scikit-learn is really simple. If we wanted, we can do it in one line of code. We need to select the selecting class, in this example, select k-best, and it will take as parameter one of the ranking metrics that we have here at the top. And then we need to determine how many features we want to retain. And then with fit transform, it will rank the features, select the top 2 in this example, and then transform the dataset to obtain, in this case, a dataset with 2 features. And in select k-best, we will find a lot of parameters where we can find the importance or the ranking of the features and which features was selected and which feature was not selected, in case we want to investigate more about what went on in this algorithm. In filter methods, we also can find multivariate methods. So these methods don't look one feature at a time, but they look at the group of features together. And a classic example is a method to determine duplication variables, variables that are identical. We probably don't need them all, we just need one of them. And the other one is to detect correlation. Correlation tells us when 2 variables are correlated, the more we have of one variable, the more we have of the other one, like we see here at the bottom. And in this case, we could say, or we could think that the 2 variables offer more or less the same information about the target, because the more we have of one, the more we have of the other. We also can have negative correlations, like the more we have of one variable, the less we have of the other, but in essence, this is the same. So they are providing data that it could be redundant. So if we have a group of correlated features, we may choose to only use one in our predictive models. Now, Feature Engine offers functionality to remove duplicated variables utilizing the fit transform functionality, and also to find and remove correlated features. With the drop duplicate features, we are going to use it just as we would use any scikit-learn transformer. With fit, it finds the duplicated. With transform, it just keeps one of the duplicated variables and removes the rest. More interestingly, if we want to drop correlated features, we can call the class drop correlated features. We can indicate the correlation method that we can use, and there are several correlation methods that we can use, like Pearson, Spearman, Kendall. They are slightly different. And then we indicate what would we consider the correlation threshold. This transformer will find a group of correlated variables. It will take one arbitrarily and will remove the rest. And this is done during the transform procedure. Now, this is the brute force analysis. We detect a group of correlated features. We take the first one and we remove the rest. But we could also do something a little bit more smartly. And in this case, we would use the smart correlation selection from Feature Engine. And here we have different ways of choosing from the correlated group of variables which one we want to keep. With the smart correlated selection, we can indicate again which correlation method we want to use, in this case Pearson, the threshold, and then we can choose how we want to select these features. So from the correlated group, let's say in our data set, we have 5 features that are highly correlated. Which one of these 5 I want to keep and which one I want to drop? One option is to keep the feature with the highest variance. So here in the selection method, we would pass variance. Another option would be to select the feature that has less missing value. And another option would be to train a small model on these features, derive the feature importance based on this model, for example, with a decision tree or a random forest, and then select the feature with the highest importance. We can also do that automatically, setting the right parameter here in the selection method. And then with fit, it finds the correlated groups and determines which one is going to keep from the group. And with transform, it drops the unnecessary variables. Moving on to wrapper methods. Wrapper methods also have some characteristics that make them wrapper methods. The first one is that they focus on the machine learning model that we want to train. So if we aim to train a random forest, the wrapper method will use a random forest to select the features. And the second characteristic is that it evaluates subsets of features. So it doesn't look at one feature individually, it looks at features in a group. And we're going to see how we select these features. So on the advantages side of the equation, these methods consider feature interaction because we are looking at groups of features and not at groups individually. It tends to return the best possible performing model, and this is because it almost examines all the possible feature combinations that are available. And for a given algorithm, in theory at least, it tends to return, or it should return, the best subset of features. On the downside, it's not model agnostic, so the features that we find are the best for a random forest may not be the best for a logistic regression. And it is extremely computation expensive to the fact that with large data sets, and even with not so large data sets, it's almost often impracticable. Now, the procedure of wrapper methods is as follows. First, we create a feature subset, and there are ways in which we can create these feature subsets, as we're going to discuss in a second. Then we train a model on this particular subset. We determine the importance and we kind of keep it for later, and then we repeat. We create another feature subset, we train another model, we determine the importance, we keep for later, and so on. So the key here is to create these feature subsets. How do we do it? And then to select the features. So there are three main paradigms to create these feature subsets. The first one is called forward feature selection. In this case, we start from one feature in the dataset, and then we add one feature at the time. But how do we do this? It will train models on all single features first. So if we have 10 features, it will create 10 models. And then we determine the performance of these 10 models and select the feature that returns the best performing model. Now we have one feature. It will add all the possible remaining 9 features, and then it will create 9 models with these 2 feature combinations, and it will select the best performing one. And then to this group of 2 features, it will add all possible feature number 3, create all the models, select the best one, and then with the 4, and then with the 5th. So as you see, this procedure creates a lot of machine learning models. The step backward selection is the same, but instead of adding one feature at a time, it just removes one feature at a time. So it starts with the entire dataset. Let's say it starts with 10 features. Then it removes one of the 10, it trains a model. Then it removes a different, it trains a model. Removes another feature, it trains a model. And then it removes the feature that returns the model with the worst performance. Now we have 9 features. Then we remove another feature, one at a time, train models, remove another feature, and so on. And the exhaustive feature selection basically creates all possible feature combinations and then trains models on them to select the one that performs the best. So if our dataset has, for example, 4 features, it will train 4 models on each individual feature. Then it will train models on all possible combinations of 2 features, then models on all possible combination of 3 features, and then a model on the 4 features. And then it will select the one that performs the best. So this method in particular is particularly very costly. We can automate the implementation of wrapper methods utilizing MLextend. This is another open source Python package. And it contains 2 classes. We can perform step forward or step backward feature selection with the SFS. And we can perform the exhaustive search with the EFS. So the characteristics of these algorithms, as I said, they are not model agnostic. So in this example here, we want to select features for a nearest neighbor classifier. So we instantiate the model, and then we pass the model as a parameter to the feature selection class. We need to indicate how many features we want to keep, and this again is arbitrary, unfortunately. There is also always some degree of arbitrarily in the feature selection procedures. And then we indicate if we want to do step forward or step backward by setting this parameter to true and false. And then it evaluates model performance. So we have the option to choose which performance metric we want to evaluate, in this case, the accuracy. And if we want this selection procedure to take forever, we can also do it with cross-validation. And then with fit, passing the train set and the target, it just performs all these computations and select the best performing features. In the case of the exhaustive search, the procedure is identical. In order to make it run faster, we can indicate what is the minimum features in our subsets, in this case 1, and what is the maximum number of features in our subset, so in this case 4. So if we have a data set with 10 variables, it will not train models with 10 variables or non-variables, because here we said that the maximum number of features that we want in each set is 4. The rest of the parameters is the same, and with fit, it will basically train all these models and determine the best subset of features. The third group of machine learning selection algorithms are the embedded methods. The embedded methods have the characteristic that it assigns feature importances when it trains the machine learning model that we want to use. So the feature selection, in a sense, is happening as we train the machine learning model. The pros about these selection algorithms is that they offer, in general, good model performance, so they tend to select good features. It captures feature interactions because it evaluates the whole feature dataset at the time. They tend to be better than filter methods, and they are faster than wrapper methods. The downside is that they are not model agnostic. So if we use a lasso, then the features selected are good for lasso. It may or may not be good for decision trees. So how do embedded methods work? First, we train a machine learning model, for example, a lasso regression. Then this model needs to have a way in which we can derive the importance. So we derive the feature importance, and then we remove the non-important features. And here we're going to use some sort of arbitrary or non-so-arbitrary criteria to remove the non-important features. The battle horse of the embedded methods is lasso. Lasso offers a penalization metric that will shrink the coefficients of variables that are not useful to 0. So if the penalization is 0, then we can remove that feature. Another way is to use decision trees or decision tree dependent models like random forest or gradient boosted machines. All of them will assign some sort of importance to the feature depending on how high in the tree the feature is used, the improvement in the impurity in the nodes, and so on. So we can derive some sort of metric of the feature importance and then select the most important features. And the same is true with the regression coefficient. So a bigger regression coefficient usually tells us that that variable has a bigger effect in predicting the target. We can perform embedded methods with scikit-learn in very few lines of code. The first one is to set the machine learning model that we want to train. In this case, we're going to use support vector machines. We need to set an algorithm that has some sort of importance metric. So we cannot use, for example, nearest neighbors. We use regression or decision trees or support vectors machine. And then we're going to use the class select from model. We're going to pass this algorithm to the select from model. And here we fit the model first. So select from model, we just select the top ranking features. And with transform, we return a data frame that contains only the most predictive features. And select from model will store information about which were the features that were selected. Now, there are also some algorithms that don't fit within one of these categories per se. They tend to have some characteristics of embedded methods and some characteristics of wrapper methods. So these are what I call hybrid methods. Hybrid methods, first, they derive the feature importance from a machine learning model, for example, from a decision tree. And then they remove or add features based on this importance. And then they will train multiple machine learning models, just like wrapper methods, and they will select features based on model performance. So they have in common from embedded methods that they do derive the feature importance, and they have in common with wrapper methods that they tend to build more than one model, and they select features based on model performance. But they are less computationally expensive than wrapper methods because we do not create an enormous amount of feature subsets. We just optimize the feature subset creation by leveraging the importance derived from the original machine learning model. There are a number of feature selection methods that are hybrid that we can use, and most of them are supported by feature engine. We have, for example, feature shuffling that I will discuss in more detail in the coming slides. We have variations of recursive feature addition or recursive feature elimination, in which we add features from the most important to the least important, or we remove features from the least important to the most important, but we don't remove all possible features, just like wrapper methods. We inform which feature we want to improve with the importance of the feature that we derived from a decision tree, for example. We can also train models just with one feature. So if we have 10 features, we create 10, for example, decision trees, and then we obtain the performance of those 10 decision trees, and then we select the features that determine the highest performing algorithms. This is also supported by feature engine in the single feature performance transformer. And we can also use the target mean encoding in order to detect the most predictive features. In this case, if we have categorical variables, for example, we replace the categories by the mean of the target, and then we take that value as if it was our prediction, and then we calculate a prediction metric with that mean value of the target and the real target that we surely have. And if the variable is numerical, we first sort it in bins, and then for each one of those bins or intervals, we determine the mean of the target, and then we use that as a prediction to determine the metric. So these are methods that were developed in previous KGD data mining competitions to select the most predictive features. Now, in the rest of the slides, I'm going to describe feature shuffling. So this technique works as follows. If we have a data set with 4 features, like I show here in this slide, each column is a feature and each row with the colors is an observation. We take the data frame and we train a machine learning model. And then this machine learning model will make a prediction based on this data, and with that prediction, we obtain the model performance. Now, in the second step, we shuffle the order of one feature. Just we take the variable number 1, and then we shuffle the order so that the observation number 1 is no longer number 1, now it's in the second position, and so on. And now we take this data, and using the model that we trained in the previous slide, we obtain a prediction. And with this prediction, we compare it with the real value of the target, and then we obtain a performance metric. And then we compare this performance metric with the original performance that we calculated with the original dataset. If the performance, when we shuffled the feature, dropped a lot, it means that this feature was important. If it didn't drop a lot, it means that the feature is kind of useless. Then we move on and shuffle the second feature, and we repeat the procedure. We take this dataset, we use the machine learning model, obtain a prediction, determine a performance metric, and see if the metric dropped or not. Then we do with the third feature, and then with the fourth feature. So by the end of this procedure, in this case, we will have 4 measures of the drop in the performance returned by shuffling this feature. And then we can select the top ranking features, in this case, the top 2, or like the way it is implemented in feature engine, the performance, we set a threshold of the performance. So if the performance drops more than a certain threshold, then we keep the feature. The way to implement it is, for example, we call a linear regression model, and then from feature engine, we select by shuffling, we import the select by shuffling transformer. We instantiate the linear model first, and then we pass this model as an argument from the select by shuffling. We determine the metric that we want to optimize. In this case, we're going to measure the performance as the R-square. We can choose any other metric that we want, as long as it is supported by scikit-learn. And then we can also do it with cross-validation. With fit, it determines the drop in performance of all the features in the dataset and selects the ones that drop the performance more than the threshold. The threshold is another parameter in this class. And with transform, we reduce the size of the data to just the features that are above this threshold. If you want to know more about the other feature hybrid selection, more about the other hybrid selection methods for feature selection that are available in Feature Engine. You can check the documentation. And as I discussed here, we can select by single feature performance. We have alternatives of recursive feature elimination or recursive feature addition, and also by target min encoding. So with this, thank you for your attention.